Today, we'll explore core challenges in distributed storage system scalability, fault tolerance, and consistency, and how Hadoop distributed file system HDFS tackles these while making critical trade-offs. We'll see why HDFS excels in specific scenarios, but isn't a one-size-fits-all solution. The first major challenge is scalability. As data grows exponentially, systems must scale without degrading performance. Bottlenecks like network bandwidth, metadata management, and uneven load distribution can cripple growth. The goal? Linear scaling, adding resources should seamlessly handle more data. Next is fault tolerance. Hardware failures aren't a matter of if but when. Distributed systems must ensure data remains available and durable despite node crashes. The objective: zero data loss and uninterrupted access, even during failures. Finally, consistency. Keeping data synchronized across thousands of nodes is complex. Here lies the CAP Theorem dilemma. You can't have strong consistency, high availability, and partition tolerance simultaneously. Systems must prioritize sacrificing one for the others. Enter HDFS, Hadoop's distributed storage engine. Built for batch processing at petabyte scale, it prioritizes high-throughput sequential reads over random access. Think terabytes of log files, not your laptop's documents. HDFS relies on a central NameNode. It's the brain, managing metadata like file paths and block locations. But it's a single point of failure. High availability setups mitigate this with a standby NameNode ready to take over instantly if the active node fails. Data nodes do the heavy lifting. They store 128 MB or 256 MB data blocks and constantly ping the NameNode with heartbeats. No heartbeat? The system flags the node as dead and triggers recovery automatically. How does HDFS scale? Horizontally, by adding more data nodes. Files split into blocks distributed across the cluster. But limitations exist. The NameNode's metadata must fit in RAM, and small files bloat metadata, causing inefficiency. For fault tolerance, HDFS uses triple replication. Each block copies to 3 nodes with rack-aware placement to survive rack outages. Downsides: 200% storage overhead and recovery isn't instantaneous. HDFS enforces write once, read many worm consistency. Data becomes visible only after closing a file, ensuring atomicity. But appends aren't strongly consistent, and real-time updates. Impossible. It's optimized for batch writes. HDFS makes deliberate trade-offs: throughput over latency, availability over strong consistency. Why? Batch analytics jobs like MapReduce need massive data streams, not millisecond responses. Compromise is intentional. Use HDFS for batch analytics, Spark, MapReduce, or cold storage. Avoid it for old databases, real-time apps, or workflows with frequent small file updates. It's a scalpel, not a Swiss Army knife. In summary, HDFS scales linearly via data nodes, achieves fault tolerance through replication, and sidesteps strong consistency for batch efficiency. It's a purpose-built system ideal for big data analytics, ill-suited for transactional workloads.